Okay, this is your last lesson of the motion topic. Please pause the video and complete the quick quiz. And pause the video to check and correct your answers. Okay, in this lesson we're going to be looking at how forces are very, very closely related to the motion that we have been learning about. So forces are directly related to the speed and the acceleration that we have spent this topic learning about. Okay, the first thing I want you to do is to have a think about what is causing each of these things to happen. So the first image is of a car getting faster and faster and faster, or accelerating. What's causing that car to accelerate? Underneath that, we've got a car that's braking. What's causing that car to brake? And then on the right hand side, we've got a skydiver. The one at the top is accelerating, is getting faster and faster and faster. And the one underneath is getting slower and slower and slower. And I just wonder what is causing those things to happen. So pause the video and have a quick think. In each case, the thing that causes an object to increase speed or slow down, so accelerate or decelerate, is a force. Now we're going to look a little bit more in detail at forces. We're going to recap what you've learned about forces in year 7. And we're going to link that to motion that we've learned about. So a force is a push or a pull that causes an object to move. It's measured in newtons, or capital N, N for newtons. Okay, let's start by having a look at the forces that act on a car. So any object with mass experiences the force of weight. Now this force is because the object is within a gravitational field, and that means that the object feels the force of weight pulling down to the centre of the Earth, or the centre of the planet. Now weight acts from the centre of the object down. Weight acts down. Weight is the force and it acts down towards the centre of the Earth. Now, if there wasn't a force acting in the opposite direction, that car would be accelerating towards the centre of the Earth. However, we know that cars don't accelerate towards the centre of the Earth, so there is a force that acts in the opposite direction. That force acts wherever the object is in contact with the ground. And so we call it the normal contact reaction force. And it acts from here up and from here up. And it acts in both of those places because those two places are where the car is in contact with the ground. Now actually there would be an arrow the other side of the car for both of the other wheels as well. That's called the normal contact reaction force. Okay, now if we assume that this car is moving, then there will be a driving force. And that's like the push caused by the engine, the driving force. Now, if there's a driving force, if this car is moving, then there are also some counter forces, some forces that are going to act in the opposite direction. One of those is friction. Friction acts wherever there is contact between the object and the surface it's travelling along. So in this case, it will act on each of the 4 wheels, and I can only draw 2. And we call that friction. And there was also going to be air resistance. As the car moves forward, it will collide with lots of air particles, and that will cause a force of air resistance. Okay, I'd like you to pause the video and have a look at these forces. Now I'd like you to pause the video and name the forces that I've covered up with blue boxes. So going down from the centre of the car, you should have weight. Then you can see two small green arrows, and they show the normal contact reaction force. Assuming the car is moving, there is a push from the engine or a driving force. Friction acts between the object and the surface, so the wheels and the road. And air resistance acts in the opposite direction to the way that the car is moving, the opposite direction to the driving force. Let's have a look at the forces that act on a skydiver. So because this person has mass, then they have the force of weight acting on them, and weight acts from the centre of the body down. So that's weight. And that's because this person has mass and they are in a gravitational field. And that means that the body, the object, is going to be pulled to the centre of the Earth. Now, acting in the opposite direction is going to be air resistance. As that person falls, they're going to come into contact with lots of air particles, and that's going to create the force of air resistance. So pause the video and have a quick look at this. And now have a go at writing the forces from memory. And check and correct that you got those correct. Make sure that when you label weight that you do it from the centre of the body. That's very important. So let's have a look at some other forces. The force in a rope or a string is called tension. Tension. This boat here has got mass, and therefore from the centre there will be the force of weight acting downwards. However, if there was only weight, then the boat would be sinking and then it would be going to the centre of the Earth. But that doesn't happen. The force that goes upwards, the opposite direction to weight, is called upthrust. So an object floating on water experiences the force of upthrust. This hot air balloon here, or this house, sorry, has got a force of weight acting down. But there's a force acting in the opposite direction, and that's called lift. So lift acts in the opposite direction. When you put two magnets near each other, they experience a force, and this force is called the magnetic force. It can be an attractive force, meaning that they are pulled together, or it could be a repulsive force, meaning they are pushed away. The one in the diagram shows a repulsive force. But either of them, they're both called the magnetic force. Pause the video and name these forces from memory. Check and correct your answers. We're now going to recap what a resultant force is. Okay, a resultant force is an overall force. And we look at resultant forces in different directions. So for example, if we first look at the up and down direction, the forces we've got acting are weight and the normal contact reaction force. Now, if you look at the size of the arrow for weight and then the size of the arrows for the normal contact reaction force, you can see that if you put both of these small arrows together, they would be the same length as the weight arrow. And that means that the forces are equal. It means that there's an equal amount of force pulling the car down as there is pushing it up. Now, I know that they're equal because the car doesn't move up or down, and therefore the forces are equal. Now, if we have a look in the side-to-side direction, the forces we've got acting are the push from the engine, or the driving force, friction, and air resistance. And if you look at the arrow for the driving force, you can see that it's much larger than the sum of the friction arrows and the air resistance arrow. And therefore I know that there is a resultant force. If there is a resultant force, then this object is either speeding up or slowing down, depending on which direction the resultant force is acting. To make this a little bit simpler to start with, we're going to have a look at the resultant force on a box. And I'm going to say that there's a force of 5 newtons pulling the box this way. And then there's a force of 3 newtons pulling the box back the other way. The resultant force is the overall force that's going to act. Given that these two forces are acting in different directions, you find the resultant force by doing the larger force take away the smaller force. So 5 take away 3 is 2 newtons, and it's going to be acting in the same direction as the 5 Newton force was. This is called the resultant force, or the overall force. Now, if there are two or more forces acting in the same direction, then to find the resultant force, we add those up. So, for the first one, the resultant force will be 10 newtons add 5 newtons, which makes 15 newtons. And it'll be pulled in this direction. It'll move in this direction. This one down here, the next one, 9 newtons this way, 8 newtons this way. Well, 9 take away 8 is 1, so there will be 1 newton of force in this direction. That's the resultant force. And this tells me that the object will be accelerating, both of these objects will be accelerating, and that's because there's a resultant force on them. This one is slightly more difficult. So on this side, we can add 10 and 9 to make 19 newtons going this way. And on this side, we can add 5 and 4 to make 9 newtons. And then when we find the resultant force, I'll do 19 take away 9, which is 10 newtons in this direction. So all of these boxes will be accelerating, they'll be getting quicker and quicker and quicker. And that's because there is a resultant force on them. Pause the video and work out the resultant force for each of these. When you do your answer, you need to draw the box, the arrow, and the number of the force. Check and correct your answers. Make sure you've got the arrows in the right direction. So if an object is accelerating, getting faster and faster and faster, or decelerating, getting slower and slower and slower, then there is a resultant force acting on that object. It might be a driving force in the terms of the car speeding up. It might be friction in terms of the car slowing down, decelerating. It might be the weight of the skydiver falling to earth, accelerating towards earth. It might be the air resistance of the parachute causing the person to slow down and decelerate. all of these. If an object speeds up or slows down, then there is a force acting on it. So we know if a force is acting on an object, it's either accelerating or decelerating. We can link this into our knowledge of speed, acceleration, and graphs. Here we have a distance time graph, and we looked at this in the first couple of lessons of this topic. A distance time graph, distance on the y-axis and time on the x-axis, shows us an object moving. This line, the first section, section 1 here, shows an object moving at a constant speed. It's moving at quite fast speed. I know that because the gradient is quite high. It's quite a steep line. I could calculate the speed. Speed is distance divided by time. So I could use my graph to find the total distance travelled in this section up here and the total time that that's taken down here. And I could work out the speed. And maybe it's something like 2 meters per second. 2 meters per second. If we see a flat line like this in section 2 on a distance time graph, this tells me that the object is not moving. It's still or stationary. Now, although in section 1 the car or the object is moving, the speed is not increasing. The speed is constant. All the way it's 2 meters per second. And so there's not going to be a force acting on it. Forces cause an object to accelerate or decelerate, so get faster and faster and faster, or slower and slower and slower. And in this case, both in section 1 and section 2, the speed is constant. 2 meters per second in section 1 and 0 meters per second in section 2. So we can say that there's no resultant force acting at the moment. Here we have a distance time graph again, distance on the y-axis and time on the x-axis. And a curve like this on a distance time graph shows acceleration. It shows the speed increasing. And I know that because the curve is really just a series of straight lines all joined together. So if you look at the red lines that I'm drawing, you can hopefully see that each line I'm drawing has a greater gradient. Each line I draw is steeper. And we know that the steeper the line, the faster the object is moving. So a curve shows acceleration. In order for an object to accelerate, there must be a resultant force acting on it. There must be something pushing it or pulling it. And so when you see a curve on a distance time graph, you know the object is accelerating. You also know that there is a resultant force acting on that object. And very similarly, we can look at deceleration as well. Deceleration is when an object gets slower and slower and slower. And I know that because, again, I can use my curve to show a series of straight lines. So at the start, this line here has quite a steep gradient. It's quite a steep line, which means it's going quite fast. The speed is quite high. If I go to the middle section over here, I can see that the gradient is shallower. Therefore, the speed is slower. So this curve on a distance time graph shows deceleration, an object getting slower and slower and slower. And the only way an object can get slower and slower and slower is if there is a resultant force acting on that object. So when you see a curve like this, you know it's deceleration, and you know that there is a resultant force acting on that object. Now we're going to look at a speed time graph. So these axes are different. This is speed on the y-axis and time on the x-axis. If we have a speed time graph, a straight line like this one in section 1 shows acceleration. That shows an object increasing its speed. I can see that after 1 second, if I go up to the line, this object has got a speed of 2 meters per second. After 2 seconds, it's got a speed of just over 4 meters per second. And so every second that's going on, the speed is increasing. So in section 1, we say that the object is accelerating. And if an object is accelerating, there must be a resultant force acting on that object. So when you have a speed time graph and you see a straight line like in section 1, you know that the object is accelerating and there is a resultant force acting on that object. Now section 2. Section 2 is a flat line on a speed time graph. I can see that this object is moving at 9 meters per second for all of this time. It's moving at a constant speed of 9 meters per second, and therefore there is no resultant force acting. In section 3, I can see that the speed is getting slower and slower and slower. And therefore I can say that the object is decelerating. Now for an object to decelerate, there must be a resultant force acting. So I know that in section 3 the object is decelerating, getting slower and slower and slower, and that there is a resultant force acting on that object. For each of these graphs, I would like you to describe the journey, and I want you to say where there is a resultant force acting. So you'll want to break up the graph into a few sections. And for each section, I want you to say what is happening and is there a force, a resultant force acting on that object. Check and correct your answers here. And if you have any bits that you don't understand, then let me know.